Good morning, dear participants. My class is on fluidized bed reactor in wastewater treatment. It is three-phase fluidized bed reactor actually, where gas, liquid, and solid three phases are present. As we know, fluidization is nothing but it involves passing a fluid through a static bed of solid particles with a superficial velocity enough to suspend the particles and cause them to behave like a fluid. When the fluid is introduced into the static bed of particles contained in a vessel at low velocity, the fluid just passes through the voids of the solid particles and the bed remains fixed, which is called as a fixed bed state. As the fluid velocity is increased, the bed expands until the particles become suspended when the drag force that the fluid exerts on the solid particles just counterbalance the net gravitational force on the particles. Net gravitational force means it is the weight of the particles minus the buoyant force on the particles as the particles are immersed in the fluid. At minimum fluidization velocity, the pressure drop across the bed equals to the weight of particles and the bed becomes completely suspended. This is the general definition of the fluidized bed and the minimum fluidization velocity beyond which the fluidization takes place. In a three-phase system, there are two different fluids. One is gaseous fluid and another is liquid fluid. The flow of these fluids may be co-current in the upward direction. Both provide the drag on to the particles to get suspended, or it may be in counter current flow where the primary phase cause the fluidization by providing drag to the solid particles. So due to the suspension of solid particles in fluidized bed, the particles are of smaller size, relatively smaller size, maybe in three-phase fluidized bed 1 millimeter to 6 millimeter particle size. So smaller particle size, high surface area for the same bed mass of solid particles compared to a packed bed is there. That means it gives a high surface area, and because of the flow of the fluid, gas and liquid, intimate contact between these three phases, gas, liquid and solid, is possible, and because of high surface area of the solids, so any solid catalyzed reaction or solid may be reacting. So a vigorous reaction takes place as far as the gas, liquid, solid fluidization is concerned. That means high efficiency of the mass transfer and reaction can be achieved in the fluidized bed reactor. As the topic of this three-phase fluidized bed, that is gas, liquid, solid fluidized bed application in wastewater treatment, let us have something about this water. As we know that 70% of the earth is occupied by water, and in that only 1 to 2% of the water, usable water, that is the fresh water, rest of the water contained in the sea. And among these fresh waters also, okay, the accessible waters are not all, only a few percentage of that is accessible for our use. And nowadays, because of all this your human-made things and industrialization, like the urbanization and industrialization. Lot of wastes or discarded materials are find their way to these surface water bodies and contaminate the surface water bodies. So harmful chemicals find their way to these these water bodies and pollute them, which are not which cannot be used for the human being or other living animals, and harmful to them. So water is essential for all living organisms on this earth, and water contamination is one of the primary issue of the current days. So that's why when we are discharging the water to natural water bodies, we should treat them to the permissible limit, then we can discharge that. Otherwise that contaminate the water, and the availability of water for the use get reduced. So different federal bodies or the countries, they have put certain stringent environmental guidelines and regulations on the discharge of the municipal or industrial wastewater, and to meet the stringent environmental guidelines and regulation, wastewater needs appropriate wastewater treatment frameworks. There are various types of treatment technologies available. One of the technology uses a 3-phase fluidized bed system, and last 30 years the interest in using the 3-phase fluidized bed is increasing gradually. If I talk about the 3-phase fluidized bed bioreactor alone, since 1980s, more than 2,500 research publications are seen on 3-phase fluidized bed bioreactors only. Other types of treatments are also there using the 3-phase fluidized bed. Why this is 3-phase fluidized bed? Because this operation is simple in its design and construction, and this 3-phase fluidized bed creates close contact between the gas, liquid and the solid in the system, having a high mass transfer rate, and contributes significant points of interest for application in physical, chemical and biochemical processes, including solid, liquid and gas phases. The importance of treatment of industrial wastewater. The wide range of wastewaters having toxic contaminants and a lack of sufficient finances for treatment causes an increase in the frequency of spreading waterborne diseases, more rapid environmental degradation taking place. The table here shows the different types of contaminants. Mainly the heavy metals are listed here: arsenic, cadmium, chromium, copper, iron, lead and manganese. Few of them are the heavy metals. Iron and manganese, these are not basically the heavy metals, but others are the heavy metals, but they have the harmful effect on the human health. So this table describes the harmful effect of these contaminants, and they are primary source from different industries. As far as arsenic is concerned, it comes from paint, metallurgical processes and textile industries. Chromium, steel alloy, cast iron alloy, stainless steel, metal plating industries, then tanning industries and mines runoff, mineral processing things it comes. The table continues with other heavy metals here: mercury, selenium, zinc, nitrate, dyes, pharmaceutical waste, phenolic compounds. And the phenolic compounds are organic compounds, mainly comes from refineries, pesticide industries, and many other organic chemical industries. Mercury from coal, mining, industrial waste, etc. As we can see from the harmful effects, these compounds are highly harmful and lethal to the human and other living animals. So the treatment of or the removal of these contaminants from the wastewater is of primary concern. Now let us see the fluidized bed reactor. The fluidized bed reactor is a contacting device that uses the principle of fluidization in its operation. Initially, the applications of a fluidized bed reactor had been limited to catalytic cracking when it was developed, combustion, coating, granulation, drying, and other chemical applications only. Later, this fluidized bed reactor was deployed for wastewater treatment. The figure here shows the basic concept of fluidized bed reactor in wastewater treatment. The wastewater is introduced into the bed of the reactor at a particular superficial velocity. Superficial velocity is nothing but the empty column velocity of the fluid that is flowing through the vessel. As if there were no solids. So what would be the velocity of the fluid if it flows through the vessel only? That is nothing but the superficial velocity. So at a particular superficial velocity, enough to suspend the supported media. So as you see in this schematic, the influent, that is the wastewater, is entering through the distributor plate. The distributor plate supports the solid particles on the bed and does not allow the solid particles to fall below. So it is a porous grid through which the influent is entering to the bed, and with a sufficient superficial velocity the particles get suspended. And in the suspended condition the treatment is there. So the contaminants are either removed or it is degraded to some innocuous end product in this bed. Then the effluent we take out, and there may be recycle of the effluent if it is not meeting the discharge standard which is necessary. Here the classification of fluidized bed bioreactor for wastewater treatment. The bioreactors are classified as two-phase bioreactors and three-phase bioreactors, then upflow or downflow bioreactors. So first classification, it is two-phase versus the three-phase bioreactor. Two-phase fluidized bed bioreactor involves liquid solid or gas solid process where fluidization is brought about by the liquid or gas. But as far as the water treatment is concerned, only that liquid is there, gas is not there. And a three-phase system involves gas liquid solid process where aeration or oxygenation is added to a typical liquid solid fluidized bed reactor. In a two-phase fluidized bed reactor, fluidization is provided by the flow of wastewater through the catalyst or biomass bed, and in a three-phase system, fluidization is provided by the co-current or counter current flow of the liquid and a gas through the solid bed. Again another classification based on the upward and downward flow. So upward fluidization versus downward or inverse fluidization in a fluidized bed reactor. Conventional fluidized bed reactors uses solid particles that are denser than the fluid phase, and fluidization is achieved by the upward fluid flow from the bottom of the reactor. But in inverse fluidized bed reactor, which was developed later to overcome some of the challenges introducing to the conventional fluidized bed reactor, where an uncontrolled growth of biomass that affect the bioparticles hydrodynamics, that means wash out of the bioparticles from the bed, which is a characteristic of the conventional fluidized bed, that is a disadvantage of the conventional fluidized bed reactor, can be avoided using the inverse fluidized bed bioreactor. In inverse fluidized bed bioreactor, particles, solid particles of density or lighter, the solid particles lighter than the liquid phase is used. The inverse fluidized bed reactor is argued to possess superior hydrodynamic characteristics than the conventional fluidized bed bioreactor. Let us see the application of fluidized bed bioreactor in wastewater treatment. The application is characterized, is classified into three categories. Either it is a physical, that is adsorption, or it is a chemical purely, the other side, advanced oxidation process, and in between there is a biological process. So three types of treatment process it is classified. And adsorption means it is in the fluidized bed adsorption. Biological, the treatment unit is fluidized bed bioreactor, FPPER. And advanced oxidation process, either it is fluidized bed Fenton reaction is there, or fluidized bed photocatalysis is there. So by this process, in the first, that adsorption, only that contaminant is removed, get absorbed into the solid matrix. But in other types, that fluidized bed bioreactor, fluidized bed photocatalysis, and fluidized bed Fenton reaction, the contaminant is degraded, or for if it is organic, to innocuous end products, that is carbon dioxide and water, and if it is inorganic, then it may be converted to a valence state which is not harmful. That is possible. So among these three types of application of fluidized bed bioreactor in wastewater treatment, let me first discuss about the fluidized bed adsorption. As we know, this adsorption is an effective and economical method for the removal of pollutants from wastewater. This is the most widely used treatment technique. Every household is having one adsorption unit. Okay, the water purifiers we are having, a carbon bed is there. So when fluidized bed reactor is used in adsorption, operational problems encountered in the fixed bed column adsorption are the clogging of the bed, then a temperature gradient, local hotspots may be there, channeling of the fluid through that means all the solid particles are not come to contact of the fluid, so that the adsorption is not effective. That is the channeling, and dead zones also there in the fixed column adsorption, which is these things are eliminated by the use of fluidized bed reactor. This table shows some of the previously published work where adsorption is used in fluidized bed for wastewater treatment. Okay, large number of publications are there, but here only a few is considered. For the phenol, copper removal, other emerging micropollutants. This next the other category is fluidized bed bioreactor. As we know, this fluidized bed bioreactor has been widely used for aerobic and anaerobic wastewater treatments. The system consists of microorganisms coated particles. That means the particles, solid particles, on to that the biomass is coated. So the coated particles of the microorganisms in wastewater which are sufficiently fluidized, these bioparticles are sufficiently fluidized to keep the phases thoroughly mixed. So intimate contact between the liquid fluid phase and the solid phase, that is bioparticles, are possible. We get a very high mass transfer and the reaction, that is degradation of the contaminant. The support materials of a fluidized bed bioreactor normally have extremely large specific surfaces and achieve treatment levels in a shorter time than the conventional biological treatment processes such as suspended cell systems. So here this table again gives the information on the published work where bioreactors are used in wastewater treatment, dyeing effluent for the removal of color and COD, metal precipitation industry for the removal of copper, lead, cadmium, zinc, aquaculture effluent, denitrification, domestic wastewater. So various applications are there, and the fluidized bed efficiently remove the contaminants, as you can see. The third is the chemical process, that is the advanced oxidation process in a fluidized bed reactor. This Fenton oxidation, one of the most effective advanced oxidation process because of its rapid formation of this hydroxyl radical in a acidic medium. The process consists of a homogeneous catalytic reaction between ferrous ion and hydrogen peroxide. So in Fenton reaction, ferrous ion and hydrogen peroxide is used to produce this hydroxyl group that can oxidize the organic pollutants. So this is basically for the organic pollutants, it is quite effective. Then photocatalytic oxidation is another advanced oxidation process where the application of a fluidized bed reactor has attracted a lot of interest to the researchers, and its use in industries are also there. In photocatalysis, a semiconductor metal oxide is used as a photocatalyst to oxidize organic pollutants to carbon dioxide and water. So here the semiconductor metal oxide generates electrons, and these electrons react with the hydrogen present in, water present in the system, produce the hydroxyl group, and that reacts with the organic compound and degrade those organic compounds to carbon dioxide and water. Here another table shows the published work in the area of photocatalyst used in the fluidized bed reactor for wastewater treatment. So dyes, hospital wastewater, COD, phenol, methyl orange, another dye. These things are removed, and it is very effective. For phenol, 100% degradation is achieved. COD removal is 98%. Rhodamine blue 96%. Rhodamine blue another, and it is 99% also it is achieved. So now a little detail in some of the case studies you will discuss the fluidized bed reactor in wastewater treatment. First is the adsorption. One case study is the simultaneous removal of multi-pollutants in the integrated flocculation adsorption fluidized bed. So simultaneous flocculation and adsorption is there. One adsorbent is there, and then coagulation of the particle to form the flux. Okay, that means the suspended particles are there also. So it is a novel integrated flocculation adsorption fluidized bed based on the hydraulic classification theory, and the operation, performance, characterization and mechanism of the novel process are described in this particular work. In this system, 150 milligram per liter, actually it is milligram per liter. So 150 milligram per liter kaolin clay and 100 milligram per liter of phenol were used to simulate the multi-pollutant in synthetic effluent. So both kaolin and this phenol are considered to be the pollutant here. So removal of kaolin and phenol is done. As you see the experimental setup, so kaolin solution tank is there, then flocculant solution, okay, it is here. So the flocculant solution is pumped into the fluidized bed by means of a pump. This is the plenum chamber, means this is the distributor section which is located at the bottom, through which with intimate mixing this enters, and you see these solid dots are nothing but activated carbon, and these are hollow dots. These are nothing but the air phase is there. So then outlet is there. So this is the way it is treated. So what is achieved here? Kaolin removal, as you see, kaolin removal efficiency is shown here. Kaolin removal efficiency percentage. So in terms of Euler's number, it is explained. In terms of Reynolds number, it is explained. The kaolin removal efficiency. So a good removal efficiency of the kaolin 80%, almost more than 80% is seen. Then this is the phenol removal, CO2, CO0. Almost you see that it is reaching the value of 100% removal is there for this phenol removal. But when it is compared with the fixed condition and the fluidized condition in the same system, at a little higher superficial velocity, the second case 8 millimeter per second, it took 310 and 230 minutes in the fluidized bed fixed bed. Obviously fluidized bed has an advantage, especially at a higher superficial velocity. Multi-pollutant removal, okay, the mechanism is mentioned here. The flocculation takes place. So these are the different colors, shows the phenol solution, adsorbent, then adsorbent with phenol adsorbed, kaolin clay slurry, solids, flux, and the turbulent direction, that means the flow, the movement of the particles. So first stage of flocculation, second stage of flocculation, then your here the adsorption is there. Next, the fluidized bed reactor in wastewater treatment, a biological process. So here I will discuss this fluidized bed bioreactor for multiple environmental engineering solutions. Then inside that I will take two case studies of my own laboratory. The fluidized bed reactors are widely used for multiple environmental engineering solutions such as wastewater treatment as well as some industrial applications. Fluidized bed reactor offers many benefits such as compact bioreactor size, traditional treatment technique of the organic pollutant are oxidation rich, oxidation pond, activated sludge system where huge space is required. But if your industry is located in such a space place where the land cost is and land availability and land cost is too high, so that's why a compact treatment system is necessary where this fluidized bed system can be used. Okay, the compact bioreactor size in the case of fluidized bed is due to the short hydraulic retention time, long biomass retention on the carrier, high conversion rates due to fully mixed conditions, and consequently high mass transfer rates, no challenging of the flow, dilution of influent concentrations due to recycle flow. But there are certain disadvantages also there with the fluidized bed reactor. It is the size limitation due to height to diameter ratio. Height requirement is much more than that of the diameter. High energy requirement due to high recycle ratio and a long startup period for biofilm formation. Only that operational constants are there. In a oxidation pond, nothing is there, open. Just you allow the wastewater to enter to the pond, just seed it, nothing to do automatic. That it takes months of time, but degradation is there. Like schematic of one such fluidized bed bioreactor is shown here. Fluidized bed bioreactors are characterized by solid biomass carrier that is suspended using high liquid and gas flow rates that allow the carrier to be fluidized and behave as a fluid. Biological treatment of organic and inorganic environmental contaminants is often challenged by their toxicity and low energy yields. Main concern in the low energy yields from the contaminant degradation to the organisms catalyzing the reactions. If low energy is there, then growth of the microorganism is not significant. So these disadvantages can be removed, or the fluidized bed reactor can overcome many of these challenges and hence have been widely studied for many applications. Here in this schematic you can see the left side that air is there and right side here air is not there. So this is anaerobic and the left one is aerobic. This is aerobic reactor. So for domestic wastewater treatment, biodegradation of recalcitrant organic compounds, that means very harmful organic compounds, reduction and oxidation of organic and inorganic contaminants, bioprecipitation of various inorganic compounds, oxidation reduction reactions, and bioenergy generation. These systems are used. Bioenergy in the anaerobic reactor, that is we produce. So here the industrial applications, few industrial applications I am just mentioning. The first full scale fluidized bed reactor in the United States was installed in the Reno Sparks wastewater treatment plant in the early 1980s. And also in the same 1980s, General Motors manufacturing facilities installed 12 number of aerobic fluidized bed reactors. In 1999, an industrial wastewater with a phenolic load of 1120 kg per day was treated using fluidized bed reactor having two towers of 9 meter diameter and a 8.5 meter height in Amsterdam, the Netherlands. In the same time frame, the most important commercial developments in the field was the startup of several anaerobic two-stage fluidized bed reactor plants for the industrial wastewater, where in anaerobic we get energy also, bioenergy. The first two plants were constructed in Delft in Netherlands and Corby in France. All the constructed fluidized bed reactor systems are highly efficient due to the high biomass concentration reaching 30 to 90 kg per cubic meter, together with the efficient gas liquid mass transfer created by high upflow of the liquid velocities reaching up to 10 meter per hour. Wide application of a fluidized bed reactor have two main reasons. The first of which is to minimize the physical limitations by providing high degree of mixing of water, solid phase, and the second is to support the microbial growth and enrichment. Therefore, fluidized bed reactor allows high substrate loading rates to enrich slow growing biomass, especially for the treatment of wastewater containing toxic chemicals treatment. This technology offers many advantages because recirculation of the wastewater dilutes the concentration of the influent to a non-toxic level of bacteria and provides completely mixed or semi-mixed conditions. The outstanding advantages of fluidized bed reactor systems include high concentration of biomass, very large surface area of biomass attachment, dilution of the influent with the effluent to reduce shock effect of toxicant spikes, as well as higher loading rates, efficient mass transfer for all treatment systems. The main thing in this fluidized bed bioreactor system, it is the biomass enrichment via immobilization of low yield microorganisms. Aerobic and anaerobic polychlorophenol degradation, iron oxidation, anaerobic ammonium oxidation, and reductive dechlorination and chloroethans are the examples of biological processes which release little energy for the biomass growth. So the challenge is the biomass growth when the energy release is less. Immobilization of microorganisms with extremely low growth yields is important for engineering applications. Immobilization can take care of this thing. Fluidized bed reactors with long sludge retention times allow enrichment of reductively dechlorinating microorganisms able to carry on the slowest reactions. Another thing that iron is a key element in the bio leaching of valuable metals from the sulfide ores. During bio leaching, iron has a key role in the bio-oxidation process affecting the microbial growth, leaching efficiency and precipitate formation. The valuable metals from low-grade sulfide minerals in bio-leaching process are solubilized with biogenic ferric ion and sulfuric acid. The final effluents from the bio-leaching process have high concentrations of dissolved iron and sulfate. So removal of iron and sulfate are necessary. So the final effluent is mainly present as a ferrous ion and has to be oxidized by acidophilic microorganisms followed by precipitation for an effective removal of the iron from the wastewater. So here this table shows how effectively the fluidized bioreactor works over the other types of bioreactor. Iron oxidation rate, the maximum is achieved 26.4 with a very low hydraulic retention time of 0.2. Okay, you can tell that packed bed also sometimes better than this fluidized bed, but here you see that the hydraulic retention time is quite large, whereas the hydraulic retention time for the fluidized bed is less. So that is the advantage of this fluidized bed reactor. Then another is the high rate of bio hydrogen production for the different bioreactor types, that is anaerobic system. The fluidized bed bioreactor, this is the sludge bucket upflow sludge bucket reactor. As you see, up to hydrogen production rate 65.5 is achieved in fluidized bed bioreactor with the hydraulic retention time of 1, whereas for a hydraulic retention time of 1 it gives a 56.6. Again, this high rate of sulfate reduction is also there. Then these reactors find the application in other anaerobic ammonium oxidation in denitrification, high rate of autotrophic denitrification, high rate of fungal fluidized bed bioreactors also. Those things I am not discussing because two examples I have shown that merit of fluidized bioreactor. Although bacteria are commonly used in fluidized bed bioreactors, the use of fungi has also received attention in recent years. Fungal bioreactors may have advantages due to their rich degrading enzymes, ability to withstand harsh conditions, loading fluctuations, low pH and nutrient tolerance. Treated pharmaceuticals and endocrine disruptor compounds also. Here this schematic shows aerobic fluidized bed reactor for ferrous ion oxidation followed by rapid mixing unit for chemical addition, settler of solids separation and aeration unit. Here is a settler where the sludge is removed. This is the aeration unit and this is the fluidized bed. Then fluidized bed membrane bioreactors are also in use. Fluidized beds are integrated with the ultra microfiltration membranes to create fluidized bed membrane bioreactors to improve the biomass retention and performance of the process, which rely on slow growing microorganisms. So it is, you can see this is the anaerobic fluidized bed reactor and this is the membrane unit is there. Again, fluidized bed biochemical systems are also there. Biochemical systems, as we know, it is the anode cathode present. So with the anode and the cathode connected electrically, and they may be separated with that of the exchange membrane by the membrane, so that selectively the flow of these things are there through that. Fluidized beds combined with various bioelectrochemical systems improve their performance. Microbial fuel cells facilitate the anodic oxidation of reduced compounds such as organics with the contaminant generation of electricity, while the microbial electrolysis cells require energy input in a form of applied voltage to generate hydrogen at the cathode. So fluidized beds have been incorporated to both anodic and cathodic components in bioelectrochemical systems. So here in these schematics, to that A shows one chamber fluidized bed electrolysis cell, whereas the right side shows a two chamber anaerobic fluidized bed microbial cell. This cathode chamber is external to the bed, but anode is there inside the bed. So these are certain applications of fluidized bed bioreactors. So the importance of this already we have understood now. Now I am taking to two case studies, very specific case studies on the fluidized bed bioreactor. One is the adsorption assisted biodegradation study of phenol in a fluidized bed bioreactor. As we know, this adsorption and biodegradation are the most important methods for removing pollutants from wastewater, especially for organic pollutants. And most commonly used adsorbent is the activated carbon, because of its high surface area and developed very well developed pore structure. Activated carbon, as you know, a porous carbon material, HR, which has been subjected to reaction with gases, sometimes with the addition of chemicals such as zinc chloride, before or during or after the carbonization to increase the adsorbent properties. Activated carbon is a partially amorphous substance, little bit crystalline, microcrystalline structure it possesses. So the activated carbon you see and the graphite you see the difference, where the microcrystalline structure you can see. Then the preparation of activated carbon, how to prepare. The preparation of activated carbons occur by physical or chemical activation. Carbonization and activation are the two important stages in the activated carbon preparation. The essential reaction taking place during carbonization of precursor material, that is the raw material used for the preparation of activated carbon, is the elimination of non-carbon elements. Oxygen and hydrogen are stripped off from the carbon precursor. Sometimes oxygen and hydrogen presence is also good, because the functional groups are there on the activated carbon that helps in the adsorption of some specific chemicals. The residual carbon atoms group into sheets of condensed aromatic system, which are often relatively irregular and disordered, leaving free interstices that may be filled or blocked by the tar deposition. So these interstices or voids are formed in the char due to the misalignment of sheets of condensed aromatic systems. So this schematic shows the activated carbon preparation. Raw material, carbonization 600 to 800 degrees Celsius, char is formed. Then physical activation, that is gasification, carbon dioxide and steam is used, 800 to 1000 degrees Celsius, you get activated carbon. Chemical activation, you do the impregnation, that means you add some chemicals, then carbonization and washing is there. The chemicals normally added are zinc chloride, phosphoric acid, potassium carbonate, etc. And the carbonization temperature is less, 500 to 800 degree Celsius, this operation is there. So activated carbon is produced. Then adsorption assisted biodegradation. Activated carbon has high adsorption capacity, can maintain its adsorption capacity for a short time. It is well known that activated carbon is also a good support media for microbial growth. Thus, biological activated carbon with the attached biomass can effectively remove organic contaminants both by adsorption and biodegradation. The biological treatment processes occurs through respiration or fermentation process, in which complex organic substances are transferred into simple compounds such as mineral salts, carbon dioxide and methane. The microorganisms such as bacteria or fungi are responsible for the biological treatment process. So this is the adsorption assisted biodegradation. And as far as the biofilm is concerned, the biofilm is described as a porous tangled mass of slime or slippery matrix. It is an aggregate of microbes in which cells adhere to each other on a surface. These adherent cells are frequently embedded within a self-produced matrix of extracellular polymeric substance, forming a voluminous and a thick layer. Biofilm EPS is generally composed of extracellular DNA, protein and polysaccharides. Water is the most significant fraction of the total mass of the biofilm. It can vary from 70 to 95%. And in the dry biofilm mass, about 70 to 90% of the polymeric substances are organic materials. This table shows some of the works on removal of adsorbents onto biological activated carbons. So the microorganisms, activated carbon, phenol, the pollutants, concentration and reference. As you see, microorganisms are Pseudomonas pictorum, then Pseudomonas putida, Micrococcus spp, Serratia MTCC. These are the different microorganisms, and the immobilized materials are activated carbon, powdered activated carbon, granular activated carbon mostly, and activated carbon fiber also used. The pollutants removed here: phenol, chlorophenol, cyanide, phenol and cyanide together, methyl isobromonyl. Okay, these are the compounds. Few references are there. Where this removal of adsorbents, that means these pollutants, by the biological activated carbons are done. Now wastewater treatment in a fluidized bed bioreactor. So the advantages of the fluidized bed bioreactor already we have discussed. The problem with that is the increase in the biofilm thickness when the microorganisms in the biofilm multiply. This limits the diffusion of oxygen to the core area. Limit the diffusion of oxygen and the organic substrate to the deeper layers of the biofilm. Starvation of microorganisms at the base of the biofilm causes detach and leads to ineffective bioreactor operation. So on the solid matrix, the biofilm layer is there, and when the layer is thin, that sufficient transport of oxygen and the nutrients are there. And when the layer, because of the population rise, it increases, the thickness increases. So to the deeper layer, oxygen is not reached or other nutrient is not reached, even if the substrate, which is nothing but the kind of food to the microorganism, that is not reached, so that those microorganisms, they die. As they die, they lost the contact from the solid surface, so washout of the biomass occurs. That is the disadvantage here. Some of the literatures on the removal of this phenol and other organic compounds in the bioreactor is shown here, and the bacteria used and the pollutants that is removed, basically the phenols and polyphenols are there, and the immobilization materials, sand particles, membrane, Like earlier it was activated carbon and carbon filters were there. Now other materials also there, calcium alginate, plastic beads, membranes, etc. are used. Then phenol biodegradation by biological granular activated carbon. So in the present study, the Foxnet cell is used as a precursor material for the preparation of activated carbon. So it is about the preparation of the activated carbon. I will discuss first, then the attachment of biofilm on this activated carbon and its use in the phenol degradation, biodegradation. So the proximate and ultimate analysis of the raw materials, as you see, the volatile matter, very high volatile matter is there, Foxnet cell. That's why it is chosen. Mainly the activated carbon is prepared from different sources. Carbon was 42% to 44% only when it was treated with the alkali, that is sodium hydroxide. What is Foxnet cell? We know that it is makhana we use. So makhana is prepared from this seed. This is the makhana. This is the edible part. Now the cell of that is nothing but the Foxnet cell. That is called Foxnet. So this is the organic waste. So from this organic agriculture waste, the activated carbon is prepared. The apparatus used is a tubular furnace. The schematic of the tubular furnace you can see here, and this is the photograph of the tubular furnace. So here this nitrogen generator is used. Nitrogen is supplied in the atmosphere. Rotameter to measure the flow rate. Gas control valve is there. Lenses are there. Ceramic tube is there. This is the ceramic tube on which the boat is kept containing the raw material. This is the horizontal tube furnace. Temperature controller and beaker, etc. are there. These are the arrangements. Then preparation of activated carbon. These are the steps followed in preparing the activated carbon. First, Foxnet cell was ground and sieved. Dried Foxnet cell was ground and sieved. Soaked with 0.5 normal sodium hydroxide solution for 12 hours. Washed with water and dried at 110 degrees Celsius for 24 hours. Then that was impregnated with 3 different chemicals: zinc chloride, phosphoric acid and potassium carbonate for 24 hours. Dried in oven at 100 degree Celsius for 24 hours. Then activation at temperatures ranging from 500 to 900 was studied with the nitrogen flow, that is inert atmosphere, of 150 milliliter per minute. And this was soaked with 0.5 normal hydrochloric acid, washed with water, dried in oven at 100 degree Celsius for 24 hours again. Then the activated carbon is prepared. So experimental value of the parameters for chemical activation is shown in this figure for different materials, how much it is used, how much impregnation ratio is used. These things are mentioned here. The characterization of the prepared activated carbon is done by elemental CHNS analysis, surface area and pore volume by nitrogen adsorption, and identification of surface functional groups by FTIR. Then structure by X-ray diffraction. Surface morphology was studied using field emission scanning electron microscopy and transmission electron microscopy. So the instruments used are mentioned here. Now a fluidized bioreactor. The schematic of the fluidized bed bioreactor to the left and the photographic view of the fluidized bed bioreactor to the right, it is there. So as you see in this schematic, one air cylinder is there, that means from air compressor, the air cylinder is there where it is stored through air regulator. Air is allowed to enter. Air with bacterial filter, it is allowed to enter. Then this side there is the storage tank of the wastewater is there, from which then to maintain the pH, actually acid base is added by means of a diffuser pump here. Then this water, contaminated water, phenolic water, is pumped to the base of the fluidization column. This is the fluidized bed reactor through one distributor plate, and this is the activated carbon there in here, so on which the biofilm attachment is there, that means biologically activated carbon. So then the air out is here, and then effluent from the bioreactor is coming, recycle is done. It is a semi-batch type of system. And when the treatment is achieved to the desired level, the treated water is taken here, or intermittently, to know how much degradation is there, sampling is done at this location. The equipment characteristic is given here, so I am not discussing in detail this equipment characteristic, but it is a laboratory scale. So the diameter is 4.9 centimeter, height is of 60 centimeter, and other parameters as you see. Superficial liquid velocity used in the range of 1 into 1.33 into 10 to the power minus 4 to 2.21 into 10 to the power minus 4 meter per second. And superficial gas velocity, still less gas velocity is used, because liquid is the primary phase here, causing the fluidization, and air is supplied, okay, to maintain the oxygen level in the reactor. The density of the particles used here 1184 kg per cubic meter. Because of the biomass loading, the particles are of this. Otherwise, ordinary activated carbon, the density will be little more. So after the preparation of the activated carbon is analyzed again. Ultimate analysis of that is done. So in the ultimate analysis, you can see the carbon percentage, how much carbon. In this case, zinc chloride activation up to 89.77. Again, your phosphoric acid activation, your carbon is reaching 68% maximum, whereas in potassium carbonate, carbon is enriched to 69.85%. Up to that it is there. So volatile matters removed, and pores are created on this material. That's why it is activated carbon. Nitrogen adsorption, desorption isotherm, that gives the information or and the calculation of surface area and the pores. So that is shown here. The BT surface area analyzer, it is done. The summary of the BT surface area: the total pore volume, micropore volume, of the prepared activated carbon with zinc chloride, and is given here as you see. So what is significant here, you see at 600 degree activation we are getting a surface area. It is a very high surface area, 2869. Okay, we are getting, yeah. Where another thing that this micropore is 2124, and the mesopore is 745. So these are the very significant results obtained for this material, prepared material. Similarly, with the phosphoric acid activation, a surface area of 2636 is obtained. And another important thing that the ratio of a micro over the surface area, you see that 77% almost it is there. Similarly with potassium carbonate, okay, the surface area obtained is comparatively less than the other activators. It is only 1236 it is obtained, but this activated carbon has some specific use because of the presence of some functional groups which are not present in case of zinc chloride activation and phosphoric acid activation. So a comparison of the porous characteristics of the activated carbons from different precursors. You see the table is given, and for the present study what we have obtained. So the maximum value earlier it was reported 2736 and followed by 2400 it was, but we have obtained with a surface area of 2869, very high surface area activated carbon prepared. Similarly with phosphoric acid and potassium carbonate also very significant values are there. So maximum it was for phosphoric acid 2081, but now we have got 2636. Similarly for potassium carbonate from other type of precursors, okay, the maximum value obtained is 1800, but we have got less value, that is 1236. Then the pore size distribution, as you see that how the pore volume to pore width, that distribution plot is there. So the characterization is done with the FTIR. You see the peaks are there corresponding to different types of functional groups and the bonds which are summarized here. So the wave number for CH 3100 to 2850, carbon it is 1620 to 1400 in this range. OH, CO, carbon triple bond, etc. These are the things for different types of prepared activated carbons. It is listed here. That means a significant amount of functional groups present on the prepared activated carbon. So then acid and basic characteristic of this prepared activated carbon, point of zero charge is determined and shown here in this table. So the surface morphology plots of the APSM is shown here. You see that this is the Foxnard cell, less porous. This is the sodium hydroxide treated Foxnard cell. You remove some of the impurities. Now the Foxnard cell, activated carbon prepared from the Foxnard cell, highly porous, you see, it is highly porous. Similarly, activated carbon, phosphoric acid, we have got like this porous structure, highly porous structure we have got, and potassium carbonate also. Potassium carbonate, this is for phosphoric acid activation. Then adsorption assisted biodegradation of phenol. The industrial wastewater containing the significant amount of phenols, as you see, phenolic resin production up to 1600 milligram per liter we get. Then your coal conversion, it is 1700 to up to 7000 we get, and in coke oven 600 to 3900 milligram per liter the effluent contains. So activated carbon can only maintain the adsorption capacity for a short time once it is available for the adsorption sites. Become exhausted by the adsorbed adsorbents, and it is well known that activated carbon is also a good support media for microbial growth. Thus, biological activated carbon with an attached biomass can effectively remove organic pollutants both by adsorption and biodegradation. Even 1400 it is not degraded, and up to 1700 it is 1750 almost flat. That means the microbes are dying at this concentration of the phthalate ester. Again, for another 10 Ks2, the same study is repeated. The degradation profile and the tolerance study is there. Why I am showing this? Because I will compare the that thing with this one, the fluidized reactor, and this is suspended cell system will be compared. So the study of the internal loop air lift bioreactor. The studies are nothing but the hydrodynamic study, that is gas hold up. Gas hold up is one of the important thing because it is a aerobic system. Then gas liquid mass transfer. Mass transfer study is also done, and biodegradation. So the schematic of the system is shown here. One is the riser, that is the draft tube, central tube. The rise is there of the fluids. Then in the downcomer, downflow of the immobilized cells are there. Okay. Then so different types of the liquid and the gas phase, liquid phase, solid phase, those are used, are mentioned in this table, and photographic view of this reactor is shown here. So without plastic beads is considered to be a support material for this. Without plastic bead, this operation of this reactor, as you can see in this video. So only that suspended cells are there, not the immobilized cell. Degradation is taking place there. But here with the plastic beads, so central zone you see that rise of the beads are there, and outer of that draft tube, these are falling in the downcomer zone. This is the working. Okay, less amount of the beads are taken intentionally because this taking the video and it won't be clear if a number of beads will be more. The hydrodynamic mass transfer and phthalate ester biodegradation study in an internal loop air lift bioreactor. Here these microbes are attached to these polystyrene plastic beads. You see these after attachment of the microbes, that is KS1 or KS2, how the ACM image, so how they look like, and this is the degradation of the dimethyl phthalate and diethyl phthalate. You see these two. Okay, one is for KS1, another for KS2, for DMP and DEP. It is there. So how much degradation is possible? Phthalate ester degradation rate. Okay, it is very less. It is, that is in milligram per liter per hour. That means per liter per hour means per liter of volume of the reactor per hour. So it is quite less, because I had shown you, it is two video I have shown. One is the immobilized cell on the plastic beads, another is the simple one. But with immobilization, you see that the middle one is for the mixed culture, and isolated one KS1 and KS2. This is KS1 and KS2. These are the things. So high degradation is achieved in the bioreactor. So gas hold up is one of the important parameter, but more is the gas hold up, more will be the oxygen available in the bed, and more oxygen available means driving force will be more for the oxygen to get transfer through the liquid to the surface of the solid, that is to the surface of the microbes. So gas hold up significantly increase with increase in the gas velocity, which is shown here, and this is related to mass transfer. With increase in gas hold up, your mass transfer rate also will be more. So you see here, this is another thing, that liquid velocity in the riser and the liquid velocity in the downcomer also in the hydrodynamic that is studied. Okay, that is not that important as we are discussing this effectiveness of the fluidized bed here. So here you see, as the gas envelope is increasing, your KLA type of mass transfer coefficient, which is significantly increased with the superficial gas velocity. So more is the mass transfer means more degradation is possible. Then batch biodegradation of phthalate esters by mixed culture in internal loop airlift bioreactor is shown for dimethyl phthalate and diethyl phthalate. Okay, you see that up to 1500 already I have shown 160 hours. Then after that the lag phase is there, degradation, complete degradation is not there, and with subsequent experimental runs, when it is repeated for a number of times, how it is decreasing. Now batch biodegradation of phthalate ester by mixed culture. This is biomass analysis, that is the growth of the microorganisms are shown here. Then biodegradation of phthalate esters by combined system, that is suspended biomass and biofilm. Biofilm means it is on the solid matrix, but as it is a recirculated system, semi-batch system, so the biomass which is getting detached from the biofilm also, okay, they are present in a suspended state. So that's why float was there in the video you have seen. So that means biomass is present and biofilm together it is there. You see that the degradation is achieved for 1500 milligram per liter of DMP in just 120 hours it is there. And for different experimental runs, effectiveness of this system for the repeated use is gradually reducing, but it is not so significant like the previous one. Similarly for the diethyl phthalate, again it is shown here. So here the effectiveness of this degradation you can see. So this is the bioreactor operation as it is getting rotated. So your treatment, you see the formation is there in the tank. I continue with the presentation. Few slides I am having only. That is fluidized bed reactor in wastewater treatment. That is the third kind, that is chemical treatment. That advanced oxidation process. So three-phase fluidized bed reactor with advanced oxidation process. Your traditional wastewater treatment methods mainly focus on moving contaminants from one medium to another, whether it is carbon adsorption, moves contaminants from liquid to solid media, gas absorbing moves contaminants from liquid to gas media, and in the last 3 decades advanced oxidation process is seen to be used with significant efficiency to remove a variety of organic pollutants in aqueous solution, and came out as the attractive options for the treating wastewater having highly toxic organic contaminants such as surfactants, pesticides, coloring matter, pharmaceuticals, endocrine disrupting chemicals. This process is the simplest, cheapest, and presently considered a potential treatment method to outperform the shortcomings of biological and chemical treatment methods to eliminate contaminants. Advanced oxidation process are the methods that generate and utilize powerful but completely non-selective hydroxyl radicals in adequate quantities, which can oxidize the significant complex chemical compounds present in the industrial effluent water. Presently, fluidized bed reactor merges with a advanced oxidation process has been concerned by numerous researchers. Fluidized bed reactor with AOP can be potential in pollutant reduction over conventional methods of water treatment, as it improves degradation and decontamination further. More, compared to other treatment techniques, requires less hydraulic retention time. Here here one table shows the three-phase fluidized bed reactor with photocatalyst slurry type. It is for industrial wastewater treatment. Different types of chemicals, contaminants have been treated. Propanol, bisphenol A, this is methyl orange, phenol, etc. Similarly, the three-phase fluidized bed reactor using immobilized photocatalyst for industrial wastewater treatment is listed here. Phenol, your crystal violet, humic acid, so many other chemicals have been degraded using this, and you see almost 100% this degradation is achieved for many of these pollutants. So three-phase fluidized bed photocatalytic reactor using Fenton process. It is actually Fenton process. So mineralization of bisphenol A by using waste iron oxide catalyst. This is one study. So the schematic of that is shown here, and the removal of total organic carbon TOC, you can see this is the profile is given. So the reaction, as you know, it is the ferrous iron reacts with this hydrogen peroxide. So hydrogen peroxide with this light, it is hydroxyl ion is produced, and this ferrous iron electron is generated, and finally by these reactions hydroxyl radical is generated. So this ferrous form interact with that of this hydrogen peroxide and generate this hydroxyl ion, and the hydroxyl ions degrade the organic compounds to final to carbon dioxide and water. Then mineralization of N-methyl 1,2-pyrrolidone with 0 valent iron is another study, where the degradation of the removal of TOC you can see. Very good removal of the total organic carbon is achieved here. Another one is the three-phase fluidized bed photocatalytic reactor using titanium dioxide as a photocatalyst. It is a semiconductor metal oxide. So metal catalyst impregnated on porous media for aqueous phenol decomposition is shown here. So the removal with different materials, mesoporous carbon only, ozone treatment, and other types like titanium dioxide on silica, etc. are shown here. So the final it is the end product. So this reaction mechanism, we are getting carbon dioxide and water here. So what is done? Titanium dioxide, this is semiconductor metal oxide with a light source. It may be UV light or visible light can be used depending upon the band gap, conduction band and valence band, so that electron is ejected. So here you can see this hydroxyl radical is generated, and okay, that carries out the reaction to final to carbon dioxide. So photocatalytic degradation of phenol by silver doped titanium dioxide nano composite photocatalyst under visible light irradiation. One study is here. So here C to C naught, you can see that the degradation. There is a comparison between the UV light source and that visible light. Visible light is working well here, and TOC removal is shown here. Titanium dioxide containing mesoporous spherical activated carbon for the removal of humic acid is used. So these are different fluidized bed reactors used in the wastewater treatment. Thank you for your patient hearing. I stop my presentation here. Actually, no system in this world is good for everything. All systems have their own merit and demerit. Pros and cons are there. For specific use, okay, different things are there. Although we are moving before 100 years, maybe bullock cart was of importance. Now bullock cart is eliminated, but it is not completely eliminated. Still, the use of the bullock cart in a specific area is there. But we have this because of the development of IC engine, we are using other types of motor carriers. We are using, okay, which is predominantly used, but that is advantages also good, but it is not completely eliminating. Similarly, when the space is available, although we are talking about the fluidized bed reactors of different kinds, even if the ordinary that oxidation bond oxidation rich systems which are there, these are the ponds in the open space containing the microorganisms, and organic wastewater enters to that. The organisms present in the nature, they have the capacity to degrade that. But when the discharge, this contaminant which is discharge is of a high concentration, that is lethal to the microorganisms, they die. That is not effective. And if we are generating a good amount of this wastewater, and your pond is not that effective because it takes months of time to degrade that. But if we are generating to a high amount, then we have to adopt some specific treatment method. And when the space is a constant, then this type of system fluidized bed bioreactors can be used. And among the fluidized bed bioreactors, the there are inverse fluidized bed bioreactor, conventional three-phase fluidized bed bioreactor, then semi-fluidized bed bioreactors are there. So every system they are having their own merits and demerits. In the conventional fluidized bed bioreactor, the particles, solid particles we are using, they are heavier than that of the liquid phase. Okay, so energy requirement in conventional fluidized bed is a little more than that in the inverse fluidized bed, where we use the solid matrix that is lighter than that of the liquid phase. But operational, there are certain operational limitations in the inverse fluidized bed there, but this conventional three-phase fluidized bed operational constant is not that as it is there in the inverse fluidized bed system. But inverse this inverse fluidized bed system should be operated at a high gas flow rate to obtain the same amount of the gas hold up